Hi, welcome to Easy Math with Nick. This is video number 3, and our topic today is the binomial theorem. And so, in contrast to my past 2 videos, this video does not require any prior knowledge of Calculus 1 to understand, as binomial theorem is an Algebra 2 topic, and also technically pre-calculus 2, depends on the school, but regardless, it does not require any calculus knowledge, so it'll be more accessible to many of you, I'm sure. So, our question today is how to expand x plus 3 to the power of 6. And so, just looking at this, you might have the urge to FOIL this out by having x plus 3 times x plus 3 times x plus 3 dot 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 a total of 6 times. I'm not going to write that all out, but that would take forever to FOIL out, I'm sure. And I don't think anybody actually wants to FOIL that out. And there's a better way. So today we're going to learn that better way, which is the binomial theorem. And so before we dive right in, let's go over why the binomial theorem is called that. So the binomial theorem is called such because it involves what are known as binomial coefficients. And so binomial coefficient takes the form n choose n. Which is visually n choose x, which is analogous to saying n choose n. That's how we express that verbally. N choose x. I keep saying n choose n. And mathematically, this indicates a combination. So n choose x equals n factorial over x factorial and minus x in parentheses factorial. So if we were to, as an example, do 5 choose 2, this would be 5 factorial over 2 factorial, 3 factorial. 3 is 5 minus 2. And so 5 times 4 times 3 factorial over 2 times 1 times 3 factorial. Those 3 factorials cancel, and 2 and 4 cancel. 2 on the top, 10 over 1 is 10. So 5 choose 2 is equivalent to 10. So that is just a quick review of a binomial coefficient. And this is as hard as the calculations get for the binomial theorem. That's the most difficult part, in my opinion. Binomial theorem is still tedious. I'll just give a warning, but it's a lot less tedious than FOILing it all out. I'll assure you that much, and we'll see very shortly. So, if we want a formula for the binomial theorem, it's going to be x plus y to the power of n can be expressed as a summation. If we start at k equals 0 to n, x to the power of n minus 1, y to the power of k, times, I'll have the binomial coefficient out in front. That makes it more clear. N, choose k, x to the power of n minus 1, y to the k. And so this is the formula for the binomial theorem, so-called formula for the binomial theorem. All right. And so as we do the calculation, then there's some major things to note here. The two exponents of both the x and the y terms are going to always add up to n, the total power that we saw here. So no matter in each, that's going to stay true no matter what. So that just helps to keep track of where you're at and what you're doing to make sure you're not making any silly mistakes. And also another fact that we'll take use of, that I'll enumerate here, is n choose k is also equivalent to n choose n minus k. So this is going to make the calculation we're about to do much easier, as we'll see. As for that example before, 5 choose 2 is also going to be equivalent to 5 choose 5 minus 2, 5 choose 3. So instead of calculating both 5 choose 2 and 5 choose 3, that would be redundant. So we just calculate 5 choose 2, and that's equivalent to 5 choose 3. So that saves some manual labor, saves some time, as we'll see. So let's jump right in. So our example was x plus 3 to the power of 6. So let's bring that back down here. Use a different color because we're starting the question now. X plus 3 to the power of 6. So that's going to equal, and we're starting here with n choose 0, x to the power of 6, 3 to the power of 0. That is our first term. And next, we're going to have 6 choose 1, x to the power of 6 minus 1, 5, 3 to the power of 1. Plus, next term is 6 choose 2, x to the power of 4, 3 to the power of 2. So, as we know here, we are, with each subsequent term, we're subtracting 1 off the x power, and we're adding 1 to the power of 3, which is in our formula up there, y. So we're going from 6 to 5, 5 to 4, and for our second term here, we're going from 3 to 1, and 1 to 2. So that's just another nice way to see where we're going with this. And if we continue, we're going to have 6 choose 3, x to the power of 3, 3 to the power of 3, plus 6 choose 4, x to the power of x squared, 3 to the power of 4, plus 6 choose 5, x to the power of 1. I'll write the 1 even though it's redundant. 3 to the power of 5. And finally, we'll have 6 choose 6, x to the power of 0, 3 to the power of 6. And so when when you've stopped is when you reach k equals 6, because you've gone to n already. So that's when you're done. And so in order to evaluate this, let's start with evaluating the binomial coefficients, because as it is right now, we're not done yet. So 6 choose 0 is going to be equivalent to 6 factorial over 0 factorial, 6 factorial, which is just 1. And that's the same thing as 6 choose 6. 6 choose 6 is going to be the same. 6 choose 6 is 6 factorial over 6 factorial, 0 factorial, which is equal to 1. So I figure I get those two out of the way. If we do 6 choose 1, 6 choose 1 is going to be equal to 6 choose 5 by this property that we have up here. So 6 choose 1 is going to be equal to 6 choose 6 minus 1, which is 6 choose 5. So this is going to be equivalent to 6 factorial over 1 factorial, 5 factorial, which is equal to 6. It's going to be 6 factorial times 5 factorial, and 5 factorials cancel, so we get 6. If we continue now, we'll have 6 choose 2, which is equal to 6 choose 4, which is going to be 6 factorial over 2 factorial, 4 factorial, which is going to be equal to 6 times 5 times 4 factorial over 2 times 1 times 4 factorial. 4 factorials will nicely cancel, and 1, 2 cancels, and we get 15. And finally, 6 choose 3 is equal to 6 choose 3, but that's redundant. We're not writing that. So it's going to be 6 factorial over 3 factorial. 3 factorial going to be 6 times 4 times, 6 times 5 times 4 times 3 factorial over 3 times 2 times 1 times 3 factorial. The 3 factorials cancel. We still have some nice canceling going on here. 2 times 2 times 5 is 20. So that's our binomial coefficients, and now we're ready to roll. So next part of our calculation here, bring it down here once more. So we're going to have 6 choose 0 times x to the 6, 3 to the 0. So that's going to be 1 times x to the 6 times 1. So that's going to be x to the 6. Plus, we're going to have 6 choose 1, which is 6 times x to the 5th, 3 to the 1. So that's going to be 18x to the 5th to the power of 5. And next, we're going to have 6 choose 2, which is 15 times x to the 4th, 3 squared. 15 times 9 is 135. We're going to have 135 x to the 4th. I'm afraid I might not be able to do mental math for all these. So we're going to have, next we're going to have 6 choose 3, which is 20 times x cubed, 3 cubed. 3 cubed is 27, so we have 20 times 27. Okay, I could do that. That's 540. That wasn't so bad. X cubed. We're going to have to go down now. Right out of the room. Next, we're going to have 6 choose. We're going backwards now. We're going to have 6 choose 4, which is 15, times x squared times 3 to the power of 4. So that's going to be 81 times 15. Cannot do that in my head, so let's write that out. I'm not going to care to do mental math here. 486. 486. Let's get rid of this now. We don't need this. I don't know why I chose to do it there, because it looks weird now. x squared plus, let me make sure I did that right, actually. 81 times 15. I'll do that one more time because I think I did that too quickly. It's always good to redo calculations just in case you think you went too quick. No shame in doing so. Yeah, what was I doing? It's 1,125. I don't know what I was doing. I think I was just doing that too quick. That does sound right. So that's much better. I was like, what? Okay, so just take a second to make sure you're not doing bogus math. And next after that, we'll have 6 choose 5 times x to the power of 1, 3 to the power of 5. So it's going to be, well, we're going to have 243 times, what, 6 choose 5? 6. 243 times 6. I'll do that down here. 243 times 6. 18. 1,458. Big numbers here. Maybe I should choose a better example. Nah. And finally, we have 6 choose 6 times x to the power of 0, 3 to the power of 6. 3 to the power of 6 is 729. X to the power of 0 is 1. 6 choose 6 is 1, so we're going to plus 729. There you go. And I think we have our answer. I'll stick it in black for contrast here. So there you go. We successfully used the binomial theorem to expand that polynomial, which I assure you is much better than foiling it all out here. This would take forever. So that's why we're not doing that. And I assure you, you don't want to watch me foil that out. I will probably make a mistake somewhere. And I think that's about it. Just to reiterate here, using this fact about binomial coefficients really shaves down calculation time, as calculating 6 choose 2 and 6 choose 4 separately is just redundant. They're equal, and we know mathematically that they will be equal. So there's no reason to do that twice. And so we were able to just say that they're equal. And to take note that in each of our steps up here, the coefficients the exponents add up to 6 in each one of these steps. 5 plus 1 equals 6. 3 plus 3 equals 6. 4 plus 2 equals 6. I think you see where I'm going with that. So that's just if they don't add up to your n, which was 6 here, that's how you know you made a mistake. So there you go. I think that's all I want to cover today. This was video 3 on binomial theorem. We went over definition of binomial coefficient to show our binomial theorem got its name. I'm pretty sure it goes by another name as well. If anybody in the comments wants to tell me, it was developed by, I think, I couldn't tell you, but the name it actually went by relates to its inventor. So I'm not quite sure what that is, but it has some more exotic name than binomial theorem, which is kind of stale in my opinion. But anybody in the comments wants to look that up, I'd be fascinated to do that, because I obviously can't be bothered to look that up on myself. So okay, that was it. Thank you.